Okay, this is class example program, unit F2, page 4. Very fundamental problem. Let's take a look at it. Okay, a fluid flows in a smooth pipe with a Reynolds number of 6,000. By what percent would the head loss be reduced if the flow could be maintained as laminar flow rather than the expected turbulent flow? Okay. So as you know that if the Reynolds number is more than 4,000, flow is usually be turbulent. And it doesn't matter if the flow of the fluid is in a smooth pipe or not. Even if the pipe is smooth, Reynolds experiment indicates that flow will usually be turbulent. Okay, so this is really a hypothetical question. Since the pipe is super smooth, so somehow, even though the Reynolds number is 6,000, you probably achieved laminar flow by doing something. Okay, some new invention or some new technology you invented, you made up with laminar flow out of Reynolds number 6,000. Okay, it's all hypothetical. If this flow is maintained, to be laminar, okay, how much head loss you can save? Okay. Obviously, this head loss really means major head loss. Okay? Major head loss is the head loss of a major component of the pipe, which is usually considered as horizontal straight pipe component. Okay? So this is the case. So let's consider this in two different scenarios. Actually, before moving on, sorry about that. Definition of major head loss. Major head loss is, this is the friction factor multiplied by the length of the pipe divided by the diameter of the pipe times velocity squared divided by 2 times g. So this is the definition of a major head loss of a pipe. Okay. So this equation can be applied for both laminar case and turbulent case. So major head loss for laminar is friction factor for laminar flow multiplied by L over D B squared over 2G. Major head loss for turbulent flow is a friction factor for the turbulent flow multiplied by L over D B squared over 2G. As you notice, the only difference between them is friction factor. Friction factor will be different depending on the flow type. If the flow is laminar, of course you know that, friction factor for laminar flow is simply 64 over Reynolds number. It just depends only on the Reynolds number. Okay? Friction factor of the turbulent flow. Well, it's not easy. You have to look up Moody chart. Okay? In other words, you need to rely on the experimental results for turbulent flow. It's not the straight answer here. But other properties, design parameters of the pipe being exactly the same thing. Length is the same, diameter is the same, velocity, gravity, all the same. So the only difference is friction factor, right? So let's just think about this. If you take the ratio of the major head loss of a laminar to major head loss of turbulent, this is essentially, if you take a ratio between them, of course, it's just a simply ratio of the friction factor of laminar to friction factor of the turbulent. Simple fact. Okay? So let's keep that in mind. So part A, let's find out if the flow is laminar. This is, like I said, hypothetical. Usually, you probably cannot have a laminar flow for the Reynolds number of 6,000. Okay? At least very difficult. Okay? In that case, even though it's difficult, maybe impossible, hypothetically, if you made it, suppose if you made a laminar flow for the Reynolds number of 6,000, you can determine friction coefficient, which is essentially 64 over Reynolds number 6,000. So friction factor is 0.01067. Okay? If the flow is turbulent, this is usually the case for the Reynolds number of 6,000. This is expected. What is the friction factor for that? Now, in order to determine friction factor, you need usually two information. What is the Reynolds number? Reynolds number is 6,000. What is the relative roughness, epsilon over d? Epsilon over d is, this is a relative roughness height, depending on the type of the pipe. If you're choosing rough pipe, this is fairly high, big body. This is the diameter of the pipe. This is the case of the smooth pipe. Okay. Smooth pipe really means that this is 0. Okay? So does that mean friction factor is 0? No. It's not true. So I'm going to go back one page back. Okay, so you'll know. So this is a Moody chart. So out of this Moody chart, you're going to figure out friction factor here. Friction factor F is given in a log scale. Actually, this is not log scale. This is a log scale. So first of all, let's take a look at this line. This is a straight line as it seems. This is a straight line, yes. This line represents the laminar flow. This one, corresponding equation is that. Okay. So this is the equation of friction factor for laminar flow. That is this straight line. Okay. Now this straight line stops here and then converted to dash dot. Where? Well, about 2,000. If the Reynolds number is 2,000 beyond, you cannot guarantee if it is laminar flow in a pipe. You're going to have a transitional flow. Okay. Now this is a particular case. You are in a 6,000 Reynolds number. 6,000 Reynolds number is usually turbulent flow. Okay? But suppose if you extend this line all the way to the 6,000, this is like hypothetically speaking, if the flow is all the way laminar up to 6,000 Reynolds number, this is how low your friction factor should be. That's what you got. Now, if the Reynolds number is 6,000, of course you expect it to have turbulent flow. And then this is a smooth pipe. So this is a smooth. So you're going to pick up the point right here, which corresponds to smooth pipe and then 6,000 Reynolds number. Then you're going to read off the value of friction factor F, in which I have 0.035. That's what I got. Let's just take a make sure once again. So what I did was this smooth pipeline closed up with this 6,000 Reynolds number right here. But 0.035. 0.035. Yes, that's what I got. Okay. Suppose if this is not the smooth pipe, you have to determine epsilon over d. This epsilon is relative roughness height. Diameter is pipe's internal diameter. So you can look up the data. Let's go back a few more pages. One more page back. So this is the equivalent roughness height epsilon. This one depends on the type of the pipe. Suppose you are looking at a concrete pipe, pretty rough, which is relatively high epsilon. Okay? Cast iron, of course, high value. Take a look at the plastic glass tube, which is very, very smooth pipe, 0. Okay. Anyways. So let's go back to here. Okay. So let's compare those two values. If the flow can be maintained to laminar, you have this much low value of friction factor. This is usually what you're going to get. Flow is usually turbulent at 6,000 Reynolds number. Okay. Therefore, as you can see here, the ratio of head loss, if it's laminar flow versus if it's turbulent flow, is friction factor ratio essentially. So let's just plug in the value here, 0.01067 divided by 0.035. Okay, this is going to be 0.305. Okay. So now, conclusion. How much percent head loss you can save? That is essentially this, HL turbulent minus HL laminar divided by HL turbulent times 100%. This is what you want, okay? So this really tells you how much percent save you have if the flow is laminar, right? So this is essentially 1 minus HL laminar over HL turbulent this is essentially ratio of friction factor. Now we know this one, this is this. So this is 1 minus 0.305 times 100%. Well, this is 69.52%. Huge value. This is the saving of head loss. So you are going to actually save about 70% of energy loss. It's huge. It is huge saving. So even though this is a hypothetical situation, suppose if you come up with some kind of special device or special invention that actually can maintain laminar pipe flow for high Reynolds number, that's going to be a huge achievement. It is going to revolutionize hydraulic system. Okay? So, let's stop here.